Have you ever stopped to wonder why the microscopic world is so, well, restless? Seriously, think about it. If atoms could just chill and exist peacefully on their own, we'd literally have nothing. No water, no air, no us. Everything around you, the device you're using to watch this explainer right now, the air you're breathing, it's all because atoms absolutely refuse to be solitary. Welcome to this explainer on chemical bonding basics. We're going to unpack the exact strategies these tiny restless building blocks use to link up and create, the entire visible universe.
Okay, let's dive into this and map out our roadmap. First, the quest for stability. Then, ionic bonds, our givers. Next up, covalent bonds, the sharers. Fourth, metallic bonds, the free movers. Then we'll look at rules, shapes, and exceptions before wrapping up with bonding in real life.
Section 1. The quest for stability.
So what's the core mystery here? Why do atoms actually form bonds in the first place? Well, to really get chemistry, you have to understand an atom's primary motivation. The truth is, most atoms in their natural state are just inherently unstable. They've got this high energy, and in the universe of physics and chemistry, high energy means volatility. It's completely chaotic. Atoms are constantly, desperately seeking a way to lower that energy. They want to achieve perfect stability, what we might call the noble gas lifestyle. Noble gases, like neon or argon, they're perfectly content and stable all by themselves. Basically, every other atom out there is striving to be just like them, searching for that elusive piece.
And how exactly do they snag this noble gas lifestyle? Well, it almost entirely boils down to one single, incredibly powerful number: 8. This represents the octet rule. The absolutely crucial point here is that atoms are highly motivated to gain, lose, or share electrons until they have exactly 8 of them sitting in their outermost shell, the valence shell. Getting to that magic number 8, that is the ultimate threshold for lowering their energy and reaching total stability.
Section 2. Ionic bonds, the givers.
Let's look at the first strategy atoms use, which is all about outright donating and stealing. Take sodium and chlorine, for example. It's a perfect mini-narrative. Step 1. Sodium has just one pesky valence electron. It desperately needs to ditch it to uncover the stable shell underneath. When it loses that electron, it becomes a positively charged ion, or a cation. Step 2. Chlorine has 7 valence electrons. It's practically hunting for just one more to hit that magic number 8. So chlorine happily steals sodium's electron, turning into a negatively charged anion. And step 3? Because one is now positive and the other's negative, these opposite charges attract each other powerfully. Boom! An ionic bond is formed, giving us sodium chloride.
It really is like a donation system. One gives, the other takes. It's a super clean transfer. And because the electrostatic attraction between that positive and negative is so incredibly strong, this whole donation system creates compounds with really high melting and boiling points. Actually, fun fact about this, while these solids don't conduct electricity well on their own, if you melt them down or dissolve them in water, suddenly those charged ions are free to move around, making them fantastic electrical conductors.
Section 3. Covalent bonds, the sharers.
But what happens when neither atom wants to completely give up an electron? Well, they compromise. A covalent bond is formed when atoms decide to cooperate and share electrons to complete their octet. Instead of a clear transfer, their electron clouds sort of overlap and merge together. And this sharing can happen in pairs of 1, 2, or even 3. Like 2 hydrogen atoms will share 1 pair of electrons for a single bond. Oxygen atoms, needing a bit more, share 2 pairs for a double bond. And nitrogen? It goes even further, sharing 3 whole pairs for a triple bond. Since these molecules are neutral and don't have that intense positive-negative rigid structure like ionic bonds do, covalent compounds generally have much lower melting and boiling points. Plus, they're usually pretty poor conductors of electricity.
But hey, sharing isn't always perfectly fair, right? And this brilliantly illustrates the difference between the 2 types of covalent bonds. On the left, we've got nonpolar covalent bonds. This is an equal sharing of electrons. It's like 2 perfectly matched tug-of-war teams pulling with the exact same strength. A hydrogen molecule, H2, is perfectly nonpolar. But on the right, we have polar covalent bonds. This is unequal sharing. Take water, H2O. Oxygen is a much larger, kind of greedier atom, so it attracts those shared electrons way more strongly than the tiny hydrogens do. This unequal pulling creates partial charges, leaving one end of the water molecules slightly negative and the other slightly positive.
To keep it simple, just think of covalent bonding like sharing resources between friends. Sometimes it's a perfectly equal split, like slicing a pizza right down the middle. That's nonpolar. But sometimes one friend just happens to eat a few more slices than the other. That's polar. But at the end of the day, the resource is still being shared rather than entirely given away.
Section 4. Metallic bonds. Free movers. Now, let's shift focus to a totally unique communal strategy used by metals like copper, iron, and aluminum. They don't donate, and they don't exactly share in small private little partnerships. Instead, they rely on what we call a sea of electrons. Metal atoms pack themselves tightly together in a lattice structure and just let their outer valence electrons wander completely freely throughout the whole thing. These electrons, they're delocalized. This incredible free-flowing sea of electrons is literally the secret behind everything we know about metals. It's why they're malleable and can be hammered into sheets. The atoms can just slide right past each other in that fluid electron sea. It's why they're shiny, and of course, it's why they're such fantastic conductors of heat and electricity. So if ionic is a donation and covalent is sharing between friends, metallic bonding is like a massive crowd sharing a pool of electrons freely. It's this completely communal strategy that provides incredible structural integrity, all while allowing energy to just zip right through it. Section 5. Rules, shapes, and exceptions. Let's zoom out a bit and explore the specific rules we use to map these relationships. Chemists actually have a whole toolbox to visualize these tiny interactions. First up, Lewis dot structures. These use simple dots placed around an element symbol to represent its valence electrons, making it super clear how bonds are going to form. Next is valency. This is simply an atom's combining capacity, basically how many bonds it can form to reach stability. Nitrogen's valency is 3, while oxygen's is 2. Then we have molecular geometry. Because electrons naturally repel each other, molecules form specific 3D shapes to keep those electron pairs as far away from each other as possible. Carbon dioxide forms a straight, linear shape. Water forms a bent shape, and methane creates this cool tetrahedral shape. Finally, don't forget intermolecular forces. Now, these aren't actual bonds between atoms, but rather weak bonus forces between whole molecules. Hydrogen bonding is a perfect example of this, and it's exactly the force that gives water its unusually high boiling point. Now, what's really interesting about this slide is that it shows nature loves to break its own rules. Remember that magic number 8? Well, the octet rule isn't absolute. There are some fascinating, rebellious exceptions. Hydrogen, being incredibly tiny, is perfectly stable with just 2 electrons. Boron, totally content with only 6. And some larger atoms, like sulfur and phosphorus, can actually hold way more than 8, forming what we call expanded octets. Section 6. Bonding in real life.
All right, let's bring all these theories together. When we put these 3 microscopic strategies side by side, the distinctions become incredibly clear. We've got transfer for ionic, sharing for covalent, and free movement for metallic. And those microscopic choices, they directly dictate real-world properties. You can easily see how that electron behavior dictates melting points: high for ionic, lower to moderate for covalent, and variable for metals. And conductivity is a dead giveaway. Ionic compounds only conduct when molten or dissolved. Covalent compounds basically never conduct, and metals always conduct. And this absolutely matters because you interact with these microscopic choices every single day. When you season your food, you're using table salt, NaCl, a perfect example of a rigid ionic bond doing its job for flavor and preservation. Every single time you take a drink of water, H2O, you're consuming polar covalent compounds that are literally essential for life. And the device you're watching this explainer on right now, it relies entirely on the strength and conductivity of metallic bonds in its wiring to even function. So let's lock in the absolute core takeaways here so you can avoid the most common mistakes. Here's your rapid-fire revision. Ionic means transfer. Covalent means sharing. Metallic means a sea of free electrons. The octet rule is all about the pursuit of stability. And polarity, that simply depends on which atom is pulling harder on those shared electrons. If you keep these distinct categories clear in your head, you'll never ever confuse a covalent sharing structure with an ionic lattice. Chemical bonding truly is the ultimate foundation of chemistry. So I'll leave you with this final provocative thought. If mastering these chemical bonds, understanding whether an atom transfers, shares, or frees its electrons, helps explain everything from the air we breathe to the solid metals we build our civilizations with, how might this foundation unlock the deeper, even more complex secrets of organic chemistry, biochemistry, and life itself? The microscopic world is restless for a reason, and you've just seen exactly how it builds our macro reality.
Keep asking questions, keep looking closely at the structures around you, and until next time, keep exploring.